Thank you everybody for being on today's webinar titled Looking at Measured Data in the Frequency Domain. My name is Eric Ostergaard. I am an application engineer with nCode, and I will be the presenter for today's topic. And I'd like to start off with a couple of questions. The first one obviously being a lead-in question with a very obvious answer, and the question is, do engineers need tools? Today's topic, we're going to be talking a lot about taking your time series data, which we can maybe in a lighthearted manner describe as a squiggly line, and look at it in a different way. We're going to be looking at its frequency content. So maybe a better question might be, do we need better tools, or do we need more tools than what we currently have? Do we need a way in which we can look at our measured time series data in a different manner? So the next question is, what is vibration? And for most of us on the call, being of a technical background, a lot of engineers here, we would probably gravitate towards number 3A, where we would describe vibration as something that is oscillating, reciprocating, or something that has periodic motion. These are the types of things that we're commonly measuring. And we need to be able to look at that in a way to describe those vibrations. Do they have certain frequency content in those vibrations? And is that frequency content important? Is it something that can perhaps lead to additional accumulated damage on our structures? So we have a couple of ways in which we can look at our time series data. We've got an example red squiggly line in the lower left of the slide here. It's been turned 90 degrees. And we can see above that we have a probability density function, which is describing essentially the density of the point count of our time series data. And with that kind of information, we could look at some simple statistics like what is the mean value, which kind of describes what our most common central tendency is. And we can look at the standard deviation, which might describe the scatter of that point distribution.
So speaking of I've heard people say that I think that's long term.
Thank you, Amanda. All right, guys, so getting back to the last item on the slide would be RMS. Yet one more way to describe some statistics about our measured data. And that would be describing how far we are from the mean, or what is the area or the energy within our signal. So these are all some statistical things that we might be looking at, but yet still doesn't really describe the frequency content of our vibration. And that's when we start looking at vibrations and resonance of our structures and how those vibrations might cause larger amounts of deflection. So this very first example that we look at here, something that's more of a larger scale, we can look at a wind turbine, and perhaps a very simplistic way of looking at this, we can come up with a single degree of freedom model that represents the mass of the nacelle at the top of the tower, and we can represent the stiffness of the tower itself. So we have M and K, and with that kind of information, we can begin to determine the natural frequency of that structure. And what we do know about natural frequencies is that at those particular natural frequencies, it really only requires a small amount of energy to get a large response. So in your measured time series data, which in this example might be something like wind loads, is there frequency content in the wind loads that is near the natural frequency of this particular structure? And if so, is that going to be a problem for us? Is it going to start to cause very large levels of deflection in the mass of our wind turbine and ultimately lead to larger amounts of damage, which could be a catastrophic failure like a collapse? Now, our structures aren't that simple. We have much more complicated structures, so we can add to that complexity and look at something like this particular building here, where we have multiple stories, and perhaps each one of these stories is represented by an individual mass. We now have an elastic body where we're representing it with lumped masses, and we have a number of different ways in which this structure can move. It's not going to simply flop back and forth like the single degree of freedom model we saw on the previous slide. In this case, we're going to have multiple mode shapes. So each one of these mode shapes is going to have a natural frequency. There's a particular mode shape associated with each one of those. All of the masses could, for example, move in phase with one another, and that might be mode shape 1. And some of the masses might begin to move in opposite directions, which might give us some of these higher order modes that we're seeing. So if we were to imagine an earthquake, for example, if an earthquake had a lot of lateral excitation to it, that might be something that could be pretty detrimental to this building. The way in which we've modeled it here, we have degrees of freedom that are lateral in nature. And if the excitations from the earthquake are at near any of these natural frequencies, either mode shapes 1 through 4, we could begin to see very large levels of deflection in this particular structure. So let's introduce the frequency domain and take a deeper look into that. What we need to do is we need to get a really good understanding of the dynamic response of our structures. The dynamic response of our structures, as it says here, can be made of superposition of many vibration modes. So if we look at the building structure we saw on the previous slide, we could introduce an impulse to that system. Maybe if it's a bracket, for example, that we're testing, we might wrap it with an impulse hammer. And depending upon where we strike that system, where the impulse is introduced, in what direction and in what manner, we can then begin to excite some or many of the mode shapes that that structure has. And the superposition of those is what we would be measuring in the time series domain. So how many of these modes are present? How many of them are significant? What frequencies are they? We need a way in which we can measure this in the time domain and then decompose it and look at those frequencies. So that's what we're going to do with the Fourier transform. This is a technique that's commonly used to take our time series data and bring it into the frequency domain. So here we see a very common red squiggly line on the left, and it is in the time domain. We have a horizontal axis that is in terms of seconds, and now we're going to transform that into a frequency domain, where we're now looking at, in this particular example of PSD, a power spectral density, it has units of g squared per hertz, and the horizontal axis is now in frequency. And we do also have the ability to go back. If we're looking at content in the frequency domain, we can do an inverse Fourier transform and reconstruct a time history that has the same frequency content. So how does this work? Fourier actually came up with this technique back in the late 1700s. It is a technique that allows you to decompose a continuous signal into numerous individual sinusoidal waves. Each one of these waves is going to have 3 properties that we can describe. We can describe the amplitude, which is for each one of the individual waves, the size or how tall these peaks and valleys are. We can describe the frequency or period. We can also describe the phase of each one of those. Perhaps another way that we can look at this might be on this particular plot here. We have this interesting 3-dimensional plot where our original signal, we can see it traced right here, is being displayed in the time domain. It has an amplitude associated with it. If we look at this 3rd dimension, however, the frequency domain, we could take this very simplified signal and perhaps represent that with a few sine waves. And in this case, we have 4 sine waves. Each one of these sine waves has an increasingly higher frequency as we go along this axis. And you can see that the amplitudes of those are also unique. We can see here the time series data. This is that original signal, very simplified example. And if we looked at the frequency content, we could see that it is composed of 4 very prominent frequencies, and that would be these sine waves right here. So our PSDs are, in most cases, not quite like this. These are very pronounced, unique, discrete peaks, whereas the PSDs we will typically look at might be more broadband. They might have a lot of frequency content in between the peaks. That's something that we would probably see more often with real measured data. But this is a really good representation of how that Fourier transform can go from the time domain to the frequency domain. Fourier sum. So when we take all of these sine waves and we add them together, we're going to create the original signal. So if we look at this square wave on the right and we ask a couple of questions, one, is it periodic? We could say yes, in fact it is. Is it a sine wave? No, it's not quite a sine wave. However, we could possibly come close to reconstructing that signal with a series of sine waves. And we can kind of see that here, where we start with a low frequency, high amplitude sine wave and continue to add in higher frequency sine waves and ultimately begin to reconstruct something that looks a little bit more like that original square wave. So let's talk a little bit about the power spectral density, the PSD. This is something I mentioned earlier. It's a very common way to look at your data in the frequency domain. It was a technique that came out of the 1940s, used very heavily with electronics engineers, that they used to help characterize noise. And they were very interested in the average amplitude of the noise at different frequencies. The y-axis, the vertical axis, is going to be some engineering units squared per hertz. A lot of times when we're looking at PSDs, it's going to be accelerometer data, although it doesn't have to be. And in that case, you'd probably see something like g squared per hertz. And if we take the square root of the area under the PSD, that is simply going to be the RMS of the original time series data. A couple of examples of time series data and their corresponding PSDs. If we look at this very first one in the upper left, we have a time history of a pure sine wave. So it's a very distinct tone quality. If we were to play this on a set of speakers, we would hear that sine tone. And if we looked at it in the frequency domain, it would have this very pronounced spike at whatever frequency this particular sine wave is at. So we're looking at something that's maybe around 1 hertz. The next one down right here, we have a narrowband process. We have a fairly narrow frequency response. In this case, maybe a little bit of modulation in there. And this gives us a peak as well, maybe a little bit wider at the base. As we move over though, we can see a broadband process. This might be pretty typical of real measured data, where we start to see multiple peaks. We start to see frequency content across a wide range. And then lastly, we see something like white noise, where the magnitude of the frequency content is constant across all frequencies. And when you look at that in the frequency domain, you would see a horizontal line. So those are just 4 different examples of time histories and what their corresponding PSDs would look like. To give you guys an idea, maybe to put some of these frequency ranges into perspective, the human ear responds to frequencies between 20 hertz and 20,000 hertz. A lot of times when we look at conducting a test, whether it's ground vehicle related or aircraft related, there's going to be certain frequencies we're looking at. So for ground vehicle applications, maybe looking at road-induced loads, this might be something that suspension components or chassis components might be subjected to. We're really talking about frequencies that are in the 1 to 30 hertz range. So It's definitely, a lot of that is below what we could hear, what the human ear could hear, but you could certainly feel some of these lower frequencies. The loading type can be described in the time domain. It can also be described in the frequency domain with the PSD. If we get into some higher frequency ones, maybe some aircraft applications, jet aircraft, we're looking at frequencies that are 10 to 2000 hertz. Many times we're describing that loading in the frequency domain as a PSD. Perhaps some of the reasons there are it's going to be computationally more efficient. For some helicopter components, we might do something a bit different. We might be describing things with something that we call sign-on random. So the random is the PSD, the random content, a lot of the random vibrations that an airframe of a helicopter might see. However, we would lay on top of that distinct sine tones that might be caused by some of the larger rotating components like the main rotors. So let's talk a little bit about doing our Fourier transform and doing this with software. We actually have to do things in buffers when we do this numerically with software. So you might have a long history of time series data, which is represented right here, that may contain more data points than buffers. And when that happens, you will see that when we get ready to determine what the frequency content is, we will extract a certain number of data points, and that is going to be in the form of 2 to the n power of data points. And we will then look at the frequency content of that first buffer. We'll then continue to proceed through our time series data and extract another segment of time series data and look at the frequency content of that. And by the time we've gotten to the end of our time series data, we now have multiple PSDs of different sections of our time series data. And if our time series data is transient, we can certainly expect these PSDs to be different. From one moment to the next in our time series data, the frequency content is changing. You can kind of think of this as sheet music or a song, where at different times in that music, you have different frequency content. You've got different instruments that are playing. And because we have these different PSDs, we have a couple of choices as to how we're going to combine those to represent the frequency content of the whole time series data. So when combining these buffers, we have two main options. We could choose to average them. So each spectral line, we're going to report an average of all the spectra. Or we could do something called peak hold. It's a bit more of a worst case scenario. Imagine, for example, taking all of those PSDs on a piece of paper, laying them on top of one another, holding it up to the light, and then taking the max value at each one of the spectral lines. There is, in fact, a third one called joint time frequency, where we can look at things in a 3D color plot. We would look at stacks of all these spectra and display them three-dimensionally, and that would give you a really good sense as to how your frequency changes in the time domain. Is your frequency transient? Let's talk a little bit about some properties that control our buffer size. To start with, the resolution is going to be driven by the sample rate of our original time series data and the buffer size. So if we take sample rate divided by buffer size, that gives us our spectral resolution. The default, when you look at a PSD like this, in most cases, the horizontal axis, that max frequency value that you see, is going to be the Nyquist frequency, which by definition is just half of your sample rate. So if I had chosen a buffer size such that my spectral resolution was 1/4 hertz, we might see a plot like this. However, I can very easily go back and change the properties for the number of points within a buffer, and that's ultimately going to give me a different spectral resolution, which may look something like this. So if I have a very long buffer size, that will give me a much peakier looking spectrum. We'll have much finer frequency resolution. If I have a really short buffer size, we're going to have a much more coarse frequency resolution. It's going to be smoothed out. So those will be some properties that you'll have available to you. We also have the ability to change the type of spectrum that we're looking at. We can choose amplitude, we can choose power, we can choose energy. These are all going to be options available inside of the frequency spectrum glyph. They are essentially telling you the same story. The y-axis magnitudes and units will be different. It's something you can expect. We saw earlier that the area under the PSD is going to be the RMS squared of our random time series data, which is constant. However, the area underneath of the amplitude spectrum is going to be variable. It's going to depend on your buffer size. So that's something that as you're processing your time series data and looking at it in the frequency domain, you can change that. You will still see, however, some of these very significant peaks that are appearing in both of the amplitude and the power spectral plots. Let's talk a little bit more about some frequency domain results. So in this slide right here, we actually have two plots. The upper plot contains the original time series data. And what we've done is run it through a frequency spectrum analysis so that we could look at the frequency content. And we end up getting something like this. So we're now looking at frequencies going all the way up to 80 Hertz. The original sample rate of this time series data was likely 160. And we start to see peaks and valleys. And these peaks are going to represent high response magnitudes at a particular frequency. And that could be caused by a number of different things. We could have an external force that is exerting force on our structure at a particular frequency. Or it might be that our structure has a resonance at that frequency. So don't automatically assume that a peak means resonance when looking at a PSD. It's going to be very difficult to tell the difference between that. In this particular plot, the highest peak is going to be right around 10 Hertz. We would call that the dominant frequency. As I said earlier, the human ear can hear 20 Hertz up to 20,000. So that dominant frequency is not something that we could hear, just to kind of, again, put this plot into perspective, but we would probably be able to hear that or feel that dominant frequency of 10 Hertz. We do have another peak that's all the way out here at 60 Hertz, which is a bit peculiar. This one being quite narrow and much larger in magnitude to the surrounding frequencies of let's say, 57 Hertz and all the way up to like 62 Hertz, might suggest that this was measured time series data that was collected maybe in North America, perhaps in an indoor lab where we have a lot of interference from the AC electricity. Perhaps it's picking up some of the noise that's coming from the fluorescent lights in the lab, which we would definitely be able to hear if we were actually present in that room. If you had turned off all the equipment, you would be able to hear that 60 Hertz hum of the fluorescent lights. So that, in fact, is probably caused by excitation, surrounding areas, causing that structure to vibrate right at 60 Hertz, and not from a resonance. And in fact, if you took this test and then moved to Europe and conducted it there, we might see that this peak would shift over to 50 Hertz. A couple of other interesting things about a PSD and looking at the frequency content of that. The PSD loses the concept of time. So if we were to actually repeat our test, the same exact test 5 times over, the frequency content will remain the same. Our frequency spectrum is going to look the same. So the frequency content and the frequency domain doesn't have any consideration of time or duration. That's an extra piece of information that you're going to have to remember or bring along as maybe something as metadata if the duration of the original time series data is going to be important for you. All right, what I'd like to do at this point is actually jump into nCode and show you guys a couple of things. I've got some sample time series data here. Hopefully everybody can see my nCode environment. And what I'd like to do is drag some sample time series data out onto the workspace. I'm going to click on that graphically. We have, if I check this arrow right here, a total of 6 channels, so I can choose to display all 6 of those. And I can maximize those as well. So what we're looking at here is accelerometer data. It looks like it's 2 triaxial accelerometers on vehicle, ground vehicle application, and we have units of Gs. What I'd like to do is navigate to this basic DSP glyph palette, and it's just short for basic digital signal processing tools, and grab the frequency spectrum glyph. This is what will allow me to perform a Fourier transform on my time series data, and then output frequency content or data in the frequency domain. I'm going to display that on an XY display. So now that we have everything attached, let's go ahead and just hit the run button. And now we can look at our 6 channels in the frequency domain. So let's go ahead and choose to display all 6. We'll go ahead and enlarge that. And many times we will flip the y-axis to a log scale. And now we can see up to just past 100 hertz the frequency content of my 6 measured channels. We can, and I'll do this so that we can actually compare, we can go into the frequency spectrum glyph and we can begin to manipulate things like the buffer size. So what I'm going to do is actually create a copy of that frequency spectrum glyph. We'll take the same time series data here and we'll pipe our frequency content over here. And in this second glyph, I'm actually going to change my buffer size. So let's go ahead and change that to something like 256 points. We will rerun the process, and now what we can see is overlaid on top the very first channel in red with the higher number of points in the buffer, and then in blue, the one with lower number of points in the buffer. So that's 1,024 data points versus 264 data points in each one of the buffers, showing us how that spectral resolution becomes less peaky when we include fewer data points in a particular buffer size. And this is going to be true for all channels. So I can use these blue index arrows and navigate through and look at all of the other 6 channels compared and see how that buffer changes. Some other things that we could do. Let's go ahead and just create a copy of this just to prove a point that if I were to increase the number of times this test is run, let's go here and change the repeat counts to 2, for example. Let's say we're going to repeat this test twice, and I want to treat it as if it's happening twice. We can now see if I just maximize this glyph, we have 2 repeats of our time series data. If we do the same exact frequency spectrum calculations, so the same buffer size, the same type that in, and run that process, maximizing our XY display, we can see that we have 2 plots. This is the frequency content of 1 repeat of my test. Here's the frequency content of 2 repeats of my test, and when they are overlaid, they are on top of one another. So this just goes to show that we have lost concept of time when we go into the frequency domain, and if we repeat that same test over and over, all we're doing is just increasing the number of buffered time series events that we look at the frequency content of, and they're all the same. So if we average them, we're going to get the same kind of information. Another thing that we can draw a comparison on, let's go ahead and take my original time series data, pipe it back into this one, and now what we can do is we can look at the difference between averaging all of the buffered PSDs and doing a peak hold. So in this second glyph, I'm going to choose peak hold. In the first glyph, we are averaging them. And if I rerun that process, what we now see is peak hold in blue and the averaged PSDs of all of my buffers in red. So the peak hold is certainly going to be a worst case scenario. It is the worst frequency in, for this particular spectral line, right around 22 Hertz, seen in one of those buffered PSDs. Whereas this would be representing the average of all of them for that particular spectral line. All right, so there were a couple of things where we compared and contrasted some things. Let me show you one last one, and that is looking at a joint time frequency analysis. This is actually underneath of the frequency glyph palette. What I can do here is look at my frequency content three-dimensionally. Let's go ahead and grab a plot that will show my data three-dimensionally. We'll rerun it. And let's maximize this. So if we look at something like a carpet plot, and we do a log scale on the z-axis, what you can see here are essentially all of the buffers, all of these frequencies at different times through our measured data. So our measured data was somewhere on the order of 800 seconds in duration, and we have stacks of different PSDs. If we were to look at the frequency content averaged, you could almost imagine rotating this slightly. Well, let's look at it from one end. There we go. There's the end in the time direction, and here's the end in the frequency direction. And now if we rotate that just ever so slightly, imagine averaging all of these together to give us our linear averaged of all of the buffers, or we could instead do a peak hold where instead of getting the average of all these peaks, we might just be grabbing this one particular one, and that would be something that occurred maybe 100 seconds in, representing a worst case peak at maybe about 5 Hertz. So there's yet another way that we can look at our time series data in the frequency domain three-dimensionally. All right, let's jump back into just the last couple of slides. And I'd like to start with a table here that allows us to compare data, advantages and disadvantages of data being displayed in the time domain and the frequency domain. So in the time domain, an advantage here, this is something that we're probably first exposed to. It has, because of that, become one of the easier ways for us to just visualize a squiggly line. It becomes very easy for us to observe transient behaviors. If we're looking at a ground vehicle application and we're looking at a speed channel or maybe an accelerometer channel, we can very easily see in the time domain if the vehicle is parked and stationary or if it is traveling over some obstacles or out on a proving ground course. We can look at multiple channels relative to one another and begin to understand the relationship of phase. Disadvantages, however, of time series data. A lot of data looks just like a squiggly line. It's really, really difficult to begin to pick out patterns and things that occur periodically. And also, if you have a long duration event, that can ultimately lead to very large data files. When we look at things in the frequency domain, some advantages there. It becomes very easy to see these patterns, these things that occur periodically. It's easy for us to pick out that 60 Hertz interference from the fluorescent lights in the lab that might show up. It's almost impossible to see that in the time domain. The data files themselves tend to be very small, and we can take advantage of a lot of averaging that we can use to understand statistics of our process. Some disadvantages in the frequency domain. We have lost the concept of time. So we look at PSD of one event, and then we look at the PSD of that event repeated multiple times. They don't look any different. Transient behaviors are lost. A lot of times we make the assumption that we have random excitations in our time series data when we start to look at things in the frequency domain, but that's not always going to be the case. So just a couple of things to keep in mind here, advantages, disadvantages of looking at things in the time domain or in the frequency domain. There are also other ways in which we can look at things that, depending on the type of structure you may have, a common one that comes to mind would be looking at things in the rotational or the position domain. Engine analysis is done quite a bit in this sense, where we look at orders, we look at things that are occurring once or multiple times per revolution of a crankshaft or a camshaft. And now I'd just like to wrap a couple things up in a summary slide on the frequency domain, just to state that all structures are flexible structures, and they will want to vibrate, and because of their mass and their stiffness and the way in which they may be constrained, they will have certain frequencies they'll want to vibrate at more. These would be natural frequencies. These natural frequencies can be easier to see when we look at things in the frequency domain. We use a Fourier transform to take our original time series data that we've acquired and look at that in the frequency domain. The Fourier transform also allows us to look at things in terms of multiple sinusoidal waves, where we've defined the amplitude, frequency, and phase of those sinusoidal waves. And a PSD is an extremely common way to look at that frequency domain data. It's going to allow us to look at vibration levels versus frequency. And with that, I'd like to conclude today's webinar.